For this question, we want to use the graph of y equals 2 to the x and transformations to sketch the graph of the exponential function f of x equals 2 to the x minus 1. Determine the domain and the range, and also determine the y-intercept and find the equation of the horizontal asymptote. So first we need to be familiar with the graph of our base function, y equals 2 to the x. So I'm going to start by plotting points on this base function. I'm going to use a standard set of points, -2, -1, 0, 1, and 2, and we'll substitute it into the equation 2 to the x. So I'm going to start down here with the easier ones, and that would give 2 to the 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the 0 power is 1, 2 to the -1 power is 1/2. When you have a negative in the exponent, to apply that negative, you're going to do the reciprocal of the base. So then 2 to the -2, we also need the reciprocal of the base and to raise it to the second power. So that would be 1/4. 1/2 squared is 1/4. I didn't raise it to the first power on this one because 1/2 to the first power is 1/2. So this gives me a set of ordered pairs that I'll plot. I have -2 and 1/4, -1 and 1/2, 0, 1, 1, 2, and 2, 4. So these points naturally connect to each other, and I'm going to follow the pattern of this curve. On the right end, the y values are going to infinity, and on the left end, the y values will continue to get closer to a value of 0 without ever reaching it. And so on this left side of the graph, it's demonstrating a horizontal asymptote. So I'm going to draw that horizontal asymptote being right on top of the x-axis, and that is the equation y equals 0, the horizontal line y equals 0. So this is the graph of y equals 2 to the x, which is our base graph. We really want to graph the function f of x equals 2 to the x minus 1 using transformations. So we've already determined that the base graph is y equals 2 to the x. And I can see that I have one transformation, this -1 here. And that transformation is subtracting a value to our function. And when we're adding and subtracting, the transformation is in the category of being a shift. Now that subtraction is taking place away from the exponent, outside of the exponent, and so we consider that to be a vertical shift. And the fact that that is a subtraction means that we're shifting down. So we're shifting vertically, which is down, and we're going to go down by 1 unit. So we're going to take all of the points on the graph of that base function and shift them down 1. So this transformation is only affecting the y coordinate because it's a vertical transformation. So if I want to think about the y values on the graph of f of x, remember I said the x values are not going to change, only the y values. All of those y values will get subtracted by 1. We're going down 1, those values get subtracted by 1. So if I take each of these y values, 1/4 minus 1, 1/2 minus 1, 1 minus 1, 2 minus 1, and 4 minus 1, these are going to give me all of the y values on the graph of f of x. So 1/4 minus 1, I need a common denominator, so I'll change 1 into 4/4. That becomes negative 3/4. And 1/2 minus 1, I need a common denominator, I'll change 1 to 2/2. That becomes negative 1/2. 1 minus 1 is 0. 2 minus 1 is 1. 4 minus 1 is 3. Visually, we can see that as well. Remember, we started off with these points. I'm going to make them a little bit bigger. These are the original points on the graph, and we're going to shift them down 1. I'll use a different color so we can distinguish. So this y value of 4 gets shifted down 1 to 3. This y value of 2 gets shifted down 1 to 1. This y value of 1 gets shifted down 1 to 0. This y value of 1/2 gets shifted down 1 to negative 1/2. And this y value of 1/4 gets shifted down 1 to negative 3/4. So the transformed graph is this graph that you see in purple, and the horizontal asymptote also gets shifted down 1. So that horizontal asymptote is now y equals negative 1. So we have graphed the function f of x equals 2 to the x. We also want to find the domain and range. So the domain of every exponential function is negative infinity to infinity, are all real numbers. So even when we do transformations on it, it will still have that domain. And the range originally was from 0 to infinity, but because we shifted it down 1, it's now starting at negative 1 to infinity. You'll notice that I used a parenthesis on the negative 1 because the asymptote is not included in the range. Your graph keeps getting closer to that value of negative 1 without reaching it. We also want to determine the y-intercept. You can see it visually right here. It is going to be the ordered pair 0, 0, but you can also go through the calculation as well. So if you take your function f of x equals 2 to the x minus 1, and you want to find the y-intercept, you're going to let x equal 0. That gives you 2 to the 0 minus 1. And that's 1 minus 1, which is 0. So you get that ordered pair 0, 0. And then finally, we want the equation of the horizontal asymptote. We've already mentioned that is y equals negative 1. So we've addressed all the questions in this problem, but one more thing we'd like to do is this is a problem coming from Mymathlab. And we want to see how we use the tools in Mymathlab to answer this question. So let me bring up the Mymathlab screen here. And we can see that the ordered pair negative 1 and 1/2 is the ordered pair on the base function. And that point got shifted down 1 and becomes the point negative 1 and negative 1/2. The ordered pair 0, 1 got shifted down 1 and became the ordered pair 0, 0. The ordered pair 1, 2 shifted down 1 and became the ordered pair 1, 1. And then we want to use the tool in Mymathlab to graph this equation. So I'm going to zoom in on this a little bit so we can see it better. I guess it doesn't get really bigger than that, maybe. There we go. So in order to graph this, I'm going to select the Exponential Tool. And with the Exponential Tool, if you click, I think you can click just about anywhere on the graph, and it's going to automatically draw a basic exponential graph. And then this toolbar on the right shows up, and there are a lot of things that we can adjust. So what you'll notice here is that at the bottom you see base. The base of our exponential in this example was 2, and if I go on the bar, I can adjust that base to be some other value, but it is defaulted to the base that is used in the question. So you can see if I adjust the base a little bit, the graph is going to change. So we want a base of 2 for our graph. We had one transformation in this, and that was a vertical shift. So I'm going to focus on this bar here where we have a vertical shift. And our shift goes down 1. And so I'm going to change that shift to having no shift to going down 1, and it moves the graph for me. And that's all we need to do on this example. We only had the one transformation. So let's save and check. And we have the correct graph. We want to answer our domain was negative infinity to infinity. We said the range was from -1 to infinity. We said that the y-intercept was the ordered pair 0, 0. Did I type something wrong? Let me try that again. Oh, okay. It doesn't want me to type an ordered pair. It just wants, you can see here, type an integer or a fraction. So we just want 0. And the equation of the horizontal asymptote we said was y equals -1. And so that's how we use the tool in Mymathlab. Under ideal conditions, a population of E. coli bacteria can double every 20 minutes. This behavior can be modeled by the exponential function. N of t equals n naught 2 to the 0.05 t, where t is the time in minutes, n naught is the initial number of E. coli bacteria, and answer the following questions. If the initial number of E. coli bacteria is 3, how many bacteria will be present in 3 hours? If the initial amount of E. coli bacteria is 6, how many will be present in 3 hours? If the initial number of E. coli bacteria is 6, how many will be present in 7 hours? So before we get started with any of the other values, let's make sure we have an understanding of this model here. So N of t represents the number of bacteria after a certain period of time. N naught, or N sub 0, is the initial amount of bacteria present. So what you start with, the number of bacteria that you start with. And then the rest of this is part of the formula. We have an exponential with base 2. 0.05 is our rate. And then we have t being the time. And it mentions here that time is in minutes. And this is a significant thing to pay attention to, because later when your question is asked, the time is given in hours, which is a different unit of measure. So we need to make some changes in order to use the model that's given. We have to be given time in minutes in order to use that model. So since we're given time in hours, we need to make that adjustment to the proper units. So in part A, the number of E. coli, the initial number of E. coli is 3. So we're going to use the value of 3 in place of N naught. And then our time is 3 hours, but it's in the wrong units. So we need to make the adjustment. So we need to know how many minutes are in 3 hours. So we can change to, so this is hours. We can change to minutes by multiplying 3 by 60 to get the number of minutes. So 3 times 60 would be 180. So when we use time in our formula, we want to use it in terms of minutes. So when we substitute in, we'll do n of 180, and that is 3 n naught, the initial amount of bacteria, times 2 to the 0.05 times 180. So we're going to type that into our calculator. We've got 3 times 2 raised to the 0.05 times 180. And we have, after 3 hours, 1,536 of the E. coli bacteria. So let's continue with the next part. In the next part, we now have an initial number of E. coli being 6. So we're going to use N naught to be 6. We're still looking at how many bacteria will be present after 3 hours, so I can use that same information. That 3 hours is 180 minutes. And so we're finding N of 180. We're going to have initial amount of bacteria being 6 this time. 6 times 2 to the 0.05 times 180. So 6 times 2 raised to the 0.05 times 180 will give 3,072. So that's the number of bacteria that will be present after 3 hours if we started with 6 bacteria. In the last part, the initial number of E. coli is 6, and we want to know how many bacteria will be present after 7 hours. So T equals 7 hours. We can change that to minutes. 7 times 60. There are 60 minutes in an hour, and that would give 420 minutes. So we want to find N of 420. And we have an initial amount of bacteria being 6, stated right here, times 2 to the 0.05 times 420. So we'll type in our calculator 6 times 2 to the 0.05 times 420. And we've got 125829112. Let me get some commas so I can say that number. That's 2,582,912 E. coli bacteria present after 7 hours. How much more will investment of $25,000 earning 4% compounded continuously for 4 years earn compared to the same investment at 4% compounded quarterly for 4 years? So we want to compare these investments, but not only compare them, but we want to see how much more an investment compounded continuously will make. So that means that we're going to do the difference of our two answers once we get them. So in order to answer these questions, we need a couple formulas. And the formulas that we're going to use are for periodic compound interest and continuous compound interest. So periodic compound interest is when you have regular intervals where you will add interest into your account. So this is what's described in the second account, where we're compounding 4% quarterly. So every quarter, interest will get added into the account, and that is a periodic interest. The other type is a continuous compound interest. And instead of waiting for these different periods of time, interest is continuously calculated and added into the account. And so we will use the formula when interest is compounded continuously. And you'll notice the first account is described as being compounded continuously. So what I'm going to do is I'm going to calculate what the investment would be if we took that $25,000 and had an interest rate of 4% continuously. And I'll also do the calculation of $25,000 invested at 4% compounded quarterly. And then we're going to be able to compare them. So going through the problem, the first thing we notice, we have $25,000 as our investment. That's going to be our principal, our initial investment, $25,000. And you can notice that in this formula for periodic compound interest as well as continuous compound interest, they both have P for principal, which is the initial investment. And then both accounts are paying 4%, and that is going to be our interest rate. And we're going to use that in its decimal form. So when you convert a percent to a decimal, a percent means per 100. So we're going to move that decimal place 2 places to the left, which is 2 powers of 10, that's 100. So percent per 100, we're moving that decimal place 2 places. So that's going to become 0.04. So in our formula, you can see that R represents the annual interest rate in both periodic and continuous formulas. And we're going to use that value of 0.04 in both formulas. And then we notice that we're going to be leaving the account alone for 4 years. So we have t being 4 years. So t is time in both formulas. And in the periodic formula, there's one more piece of information, the number of compoundings in 1 year. And we're going to get that value from the fact that this account is compounded quarterly. So if it's compounded quarterly, that means that interest is added quarterly or 4 times a year. So we're going to use 4 as the value of n. So now we're ready to use both formulas in the calculation. So we're going to find let's do the periodic account first. We'll say the quarterly one. And we have $25,000 as our principal times 1 plus 0.04 over 4 to the 4 times 4. There's a lot of 4's in that one. We're going to need to use our calculator to work that out. And then we're also going to figure out the investment if it were compounded continuously. And that's using this formula here, A equals P e to the RT. So we'll use $25,000 for P. E is a letter, but it's not a variable. E is the approximately the value 2.718. And it is used in this formula. It's used in lots of formulas related to exponential functions. The 25,000 e to the 0.04 times 4. That's the rate times the time. So I'll pull up my calculator. And let's see if I can make it a little bit smaller so I don't cover up those formulas. We've got 25,000 times 1 plus 0.04 over 4 raised to the 4 times 4. And that investment would pay $29,314, and we'll round to the nearest cent, so that's 47 cents. So 29,314 and 47 cents. And let's bring our calculator back up and do the other calculation. So that's 25,000 and we want e to the 0.04 times 4. That's $29,337. And once again, we'll round to the nearest cent, so that's 77 cents. 29,337 and 77 cents. So you can see that the investment that is compounded continuously earned more money, and this question wants to know is how much more. So we want to calculate the difference between these two investments. So we're going to do 29,333 and 77 cents minus 29,314 and 47 cents. And let's bring our calculator back up. This calculator has a nice feature where you can use the previous answer. So I'm going to hit second and this negative button. That's going to take the previous answer. Maybe I shouldn't do that because of our rounding. Let's not do that because of the rounding. So we're going to do 29,337.77, and I can see that I wrote down on my whiteboard the wrong value. So there should be a 7 here and a 7 here. And we're going to subtract 29,314.47. And that gives us a difference of $23.30. So if we compound continuously, if we continuously add interest rather than periodically add interest, our account will grow faster. In this question, we want to use the properties of logarithms to expand the logarithmic expression. Whenever possible, evaluate the logarithmic expressions. So since we want to expand the logarithmic expression, we're going to use some properties associated with logarithms. These properties are called the product rule, the quotient rule, and the power rule. So each one of them provides us with some flexibility on how we expand. So the product rule is going to allow us to expand when we have a product inside of the log, and that product expands to be the sum. The quotient rule is for when you have division, and it expands to become subtraction. And the power rule allows us to simplify a power on something inside of a log. And the way we simplify is that power becomes the coefficient of the logarithm. So the expression that we're working with is log of square root x over 1,000 y to the third power. So when I'm using these properties to expand, the first thing I want to take note of is any products or division. And so I'm going to focus on having one factor in the numerator, and then I have two factors in the denominator. So when I have a factor, I'm going to write an individual log with that factor. And any of the factors that come from the denominator will have a negative in front of those instead of a positive. So that means that I'm going to be able to expand this. Let me get a little bit more space. I'm going to be able to expand this into 3 individual logs because of those 3 factors that I have inside of my expression. So I have log of square root x, log of 1,000, and log of y cubed. Maybe I should erase those markings so you can see the problem. And these 2 factors that came from the denominator will have minuses in front of them, and the factor of square root x came from the numerator, and so we want that log to be positive. I don't need to write a plus sign before it. So we've applied both the product rule and the quotient rule to expand the log. And we have some opportunities for more simplification. You'll notice that on this last log we have a power, so we're going to be able to use the power rule. But in addition to that, sometimes we forget that radicals can also be written as powers. So I can rewrite that square root to be x to the 1/2. Square root of x and x to the 1/2 have the same meaning. So the first term and the last term both have powers, and I'm going to use the power rule to simplify them. And this term in the middle is log of a number, and I'm going to try to simplify that expression. So let's start with applying the power rule. So with the power rule, it allows us to take this exponent and write it as the coefficient of the log. Let's do that with both of them. So that gives 1/2 log of x minus log of 1,000 minus 3 log of y. So now I'll work on simplifying this log of a number, log of 1,000. And whenever I'm simplifying this, I'm going to use a process that helps me get to the answer a little bit easier. Logs seem a little bit confusing, but every log equation can be written as an exponential equation, and exponential equations are much more familiar and comfortable for me. So I'm going to say I'm not sure what this log expression equals. Let it equal p for power. And then you're going to rewrite this log equation as the equivalent exponential. The way you do that is you first want to identify the base. So you start with the base. The base of the log is usually written right here. And we don't have one written down, so the base of the log is usually written in a smaller font, and lower, we call that a subscript. And with this one, we don't have a base written, and when we don't have a base written, we assume it to be base 10. So this is the same as log base 10 of 1,000 equals p. We call base 10 the common log because we have 10 fingers and our number system is base 10. And once we identify that base, the base of the log will be the base of the exponent. So the base of our exponent is 10. The exponent is what the log equals, and that's why I use the letter P for power, because sometimes we call exponents powers. And then the exponential expression will equal what we have inside of the log, so that's going to be 1,000. And now that this is written in exponential form, I'm much more comfortable with figuring out what that value of p is. We think 10 to what power equals 1,000, and that's 10 to the third power equals 1,000. And now we know the value of p. The value of p is 3, and p is the value of our exponential. So log of 1,000 is 3. And we can write this as 1/2 log x minus 3 log y. On this question, we want to use the properties of logarithms and the logarithmic property of equality to solve the logarithmic equation. The equation that we're working with is log base 3 of x plus 6 minus log base 3 of x plus 2 equals log base 3 of x. So we want to use the property of equality or the one-to-one property of logarithms. Different sources name this property differently. This book that we're working with uses the property of equality. And what this property of equality says is that if you have the log base b and on the other side of the equation log base b, so I have the same log, same base on both sides, then this property says that what's inside the log on the left has to equal what's inside the log on the right. So it allows us to remove the logs from the equation, creating a much simpler equation to solve. So we really want to be able to use this property here. When we look at the equation that we have, here's our equal sign. And on the right-hand side of the equal sign, I do have a log with base 3. So it looks very similar to the right-hand side of our property. However, the left-hand side of our equal sign doesn't have just a single log, it has multiple logs being subtracted in this case. It is good that we see log base 3 on all of them, which matches the log base 3 on the right. So eventually we will be able to use that property of equality because all of the logs have the same base. So we need to resolve having multiple logs on the left-hand side here. And that's where it comes into play, these properties that I have down on the bottom here. These are log properties that we can use for either expanding or condensing. And in this case, we want to condense. We have multiple logs, and we want to condense them into a single log. So you'll notice here I have subtraction in between the logs. And so I'm going to go down to the property that we're going to use that has subtraction right here. So when we have subtraction of two logs, we're going to be able to condense them to a single log using division inside of the log. So that's called the quotient rule for logarithms. And so the way we're going to write the left-hand side, both of them have base 3. So we're going to write one log with base 3. And inside that log, I'm going to do division because we have subtraction of two logs. In the numerator, we use the log that is positive, x plus 6. And in the denominator, we use the log that is negative, the x plus 2. And you don't use the whole log, you just use what's inside the log. So our left-hand side can be condensed using the quotient rule to log base 3 of x plus 6 over x plus 2. And the right-hand side, we didn't need to do any condensing to. So we have used that quotient rule to condense. And now we have a log of base 3 on the left and a log of base 3 on the right. And we can apply that property of equality and say that what's inside the log on the left has to be equal to what's inside the log on the right. So x plus 6 over x plus 2 is equal to x. So it allows us to get rid of those logs in the equation. And now we have an equation that we're more familiar with that doesn't have logs. So I'm going to transfer it over to the right-hand side here. We have x plus 6 over x plus 2 equals x. We're going to solve this by multiplying both sides by the denominator. So I'll multiply the left by x plus 2. And I'll multiply the right by x plus 2. That's going to clear the fractions or cancel the denominator, leaving me with x plus 6 on the left. And on the right, I can use the distributive property to get x squared plus 2x. And now that I've gotten rid of that denominator, I can see that I have a quadratic equation that's got this squared here. Is how I know it's quadratic. I'm going to move all the terms to the same side and see if I can factor. So I'll subtract x and subtract 6. That gives 0 equals x squared plus x minus 6. I can factor. To get x times x is x squared. 2 times 3 is 6. And I'll do a plus on the 3 and the minus on the 2. I'll set each of these factors equal to 0. X minus 2 is 0. X plus 3 is 0. And that gives x equals 2 and x equals negative 3. So we do have some values for x, but we're not done solving this question yet because log expressions have domains that are restricted. And what that means is that you're not allowed to plug just any number into logarithms. When you have a log, for instance, log base 3 of x, you're only allowed to substitute x's that are positive. Log of 0 is undefined and log of a negative is undefined. So anytime you solve an equation that involves logarithms, once you get your values of x, you need to check to make sure your values of x are in the domain of the original equation. So I'm going to start by checking x equals 2. So x equals 2 gives log base 3 of 2 plus 6 minus log base 3 of 2 plus 2 and log base 3 of 2. And what you're going to check is inside each log you should have a positive value. 2 plus 6 is a positive 8, 2 plus 2 is a positive 4, and 2 is positive. And so we're going to be able to keep the solution of x equals 2 because it's in the domain of every log expression. We'll do the same thing for x equals negative 3. So we're going to check x equals negative 3, and that gives log base 3, negative 3 plus 6, minus log base 3 of negative 3 plus 2, equals log base 3 of negative 3. So I'm checking each expression inside the log. The first one, negative 3 plus 6, is a positive 3. Negative 3 plus 2 would give you a negative 1. So that expression would be undefined if we substituted a negative 3 in, and as well as this one here. And so that means that negative 3 cannot be a solution to this log equation, and we're going to exclude it. So the only solution to this log equation is x equals 2. On this question, we want to use the properties of logarithms to rewrite the expression as a single logarithm. Whenever possible, evaluate the logarithmic expressions. The expression we're working with is log base 4 of 192 minus log base 4 of 3. So first we want to write the expression as a single logarithm using the properties of logarithms that you see listed down here. Now in my expression I notice a minus sign, and in my properties there is one expanding and condensing property that has a minus, and that is the quotient rule. So I'm going to use the quotient rule to combine, and when we condense this to a single logarithm, we're going to condense it with division. So we can write this as log base 4. And by the way, we can only condense when the bases are the same. So if the bases are different, you wouldn't be able to use this property, the quotient rule. So when we condense to a single logarithm, we're going to use division. I'm using division because of the subtraction. If it were addition, we would use multiplication in the product rule. So we're going to do 192 divided by 3. And let me double check that with my calculator. 192 divided by 3 gives 64. And we'll notice here that it also mentions, whenever possible, evaluate the logarithmic expression. So this logarithmic expression has a number inside of the logarithm, meaning that I'm going to be able to, or at least try to simplify this more. So I'm going to think log base 4 of 64. I'm not sure what that equals. Let me let it equal some value of p. I'm going to rewrite this equation in exponential form because it's easier for me to think in exponential form. So I'll write this as a base of 4 to the power p equals 64. And even if I'm not able to do this in my head, I can bring up my calculator and start thinking 4 to the second power, that's 16. 4 to the third power, oh, that gives me 64. So 4 to the third power is 64. And that must mean that my power is 3, and this log expression equals 3. So log base 4 of 64 is 3. So that entire expression, log base 4 of 192 minus log base 4 of 3, simplified to be 3. Thank you for checking out my videos. Have a great day.